13 packet students be able to construct the Maclaurin polynomial by using substitution and multiplication. We don't start with this, but that'll end up being our goal for today. We'll practice it several times. I like to teach the Taylor polynomials early. I like to talk about polynomials early and often so that when we get to today, you look at me like, this isn't new. And it really, I don't think it should be. I think you're good enough at this that this doesn't have to be our first day for this. So it says that a Taylor series centered x equals c has these x minus c's in them. And here's our sigma notation that we have for the series. So they're saying here, this is the first day for this, but I've already started to show you sigma notation. And if we're doing nth term anyway, it's not a big leap for sigma notation. All right. So it says if c is equal to 0, then it's not a Taylor, it's a Maclaurin. So it's really important to know that it's the other way around. If you see Maclaurin in the instructions, you should know that it's centered at 0. So the other way around is the more important piece. Find a Taylor series for f of x equals e to the 5x centered at c equals 2 on the first 4 non-zero terms and the general term. And we'll throw in sigma notation just for good measure. So f of 2 is equal to e to the, let's write the equation there, the function. It says e to the 10th. And then f prime of 2 is 5e to the 5x, and that's 5e to the 10th. Second derivative is 25e to the 5x, 25e to the 10th. We're going first 4 non-zero, and there aren't any 0 terms, so we're just doing the first 4 terms. 125e to the 5x is 125e to the 10th, because we're plugging in 2 every time. And that's probably enough terms. We don't go farther than that, because hopefully by now we kind of see the pattern and what's going on. So p sub n, not really of 3, we're looking at the polynomial, not the polynomial, but the series, all of them, is e to the 10th plus 5e to the 10th times x minus 2 plus 25e to the 10th, x minus 2 squared over 2 factorial, and then 125e to the 10th, x minus 2 to the 3rd over 3 factorial. That's what we were asked to write. And we're going to put plus dot dot dot. Plus, and now we're going to write the nth term. Seems reasonable to start this at 0. So I'm going to make a little note that I'm starting at 0. All of them seem to have e to the 10th. It's not alternating. So e to the 10th. 5 to the n, they're all powers of 5. Looks like x minus 2 to the nth, because it's going 0, 1, 2, 3. And then we're over n factorial. 0 factorial, 1 factorial, 2 factorial. We just don't write the 0 and the 1 factorial. Well, if we've done the nth term, we've essentially done the sigma notation. Now, sigma notation just says where we're starting and we're going to infinity. So e to the 10th, 5 to the n, x minus 2 to the n, over n factorial. We've done all the work. We got it. Is that good? People still writing now? Okay, yep. Don't be afraid to stop me.
Yeah, but this might be a dumb question,
Nope.
but
Go ahead.
if it's n factorial on the bottom for n equals 0, how would that work?
What do you mean?
Because wouldn't you be dividing by 0? Is
0 factorial is 1.
Okay, yeah, sweet.
Now, the way that I explain it is if you have, it's with choices. And factorial is tied in with how many choices there are. For example, if there's 20 people in here, and I want to know how many combinations there are, if I choose like a batting order, it would be, well, I have 20 choices for the first spot, I have 19 for the second, I have 18 for the third. And then fundamental counting principle says you multiply all those together. The 0 factorial says how many ways are there to pick nobody. And there is one way to do that. You just don't pick anybody. That is a way to pick nobody. So that's kind of a reason why 0 factorial is 1. That's the way I explain it. All right. There are at least three, and there's more. I'd like you to know the natural log of 1 plus x. I'd like you to know 1 over 1 minus x. That's geometric. But you have to know these three. There are three special Maclaurin series you must know. These are the series for e to the x, sine of x, and cosine of x. We're going to practice this several times today. So after today, you should be even a little bit better at this. So Maclaurin series is centered at 0. So for e to the x, all the derivatives of e to the x are e to the x. E to the 0 is all 1s. So it's 1 plus x squared over 2 factorial, x to the third over 3 factorial, plus keep on going. That's x to the n over n factorial. Thank you. Oh, yeah. Here. We are on page 17 of the packet. And then this is what we'll do. Cosine, as I've said before, is an even function, so it better have even powers. So that's 1, because it's 1x to the 0. And you have to remember that cosine alternates. X squared over 2 factorial, x to the 4th over 4 factorial, x to the 6th over 6 factorial. Keep on going. If we start at 0, then we'll have negative 1 to the n, x to the 2n, I think, right? Yeah, because it's going by 2's. And then that's going to be over 2n factorial. There was a great question this morning. What about the parentheses in the denominator? And here's what I said. If you have 2 times 3 factorial, that's 2 times 6, that's 12. If you have 2 times 3 factorial, that's 6 factorial, that's 720. So there's a big difference between having those parentheses and not having it. When you don't have it, it means only the n is the factorial. Then you'll have a completely different answer. All right, sine is odd. So we need the odd powers. So the first odd power is x to the first. You have to remember that this alternates. Plus x to the 5th over 5 factorial, x to the 7th over 7 factorial. Keep on going. If we start with 0, do I want to start with, I'll start with 0, that's fine. Negative 1 to the n, that'll work. X to the n plus 1, because if I plug 0 in, I want the value to be 1. Over 2n plus 1 factorial. So there's the general term for sine. You have to know these three. If you don't, and this ends up being on the test, you're going to run out of time if you have to do this the long way. Everybody good? Here we go. You can manipulate these three special series, or any series we are given, to find other series by using the following techniques. Substitute into the series. Multiply or divide the series by a constant and or a variable. Add or subtract, and then finally integrate or differentiate. Find the Maclaurin series for f of x equals sine of x squared. Let's start with sine of x. We just did that one. X minus x to the 3rd over 3 factorial. X to the 5th over 5 factorial. X to the 7th over 7 factorial. Sine of x squared is a replacement of x. So x got replaced with x squared. That's what we're going to do over here. So we're going to put x squared in for x. And on the next one, we're going to replace x with x squared, but that's x squared to the 3rd. So this is x to the 6th now over 3 factorial. X to the 10th over 5 factorial. X to the 14th over 7 factorial. Keep on going. That is a replacement. They call it a substitution into the series. we need, let's say we're going to start at 0. So we're going to have, this alternates. So -1 to the n will start our series out at positive. That's good. The powers of x are increasing by 4. So this is an arithmetic sequence of numbers. I think of arithmetic as being linear, and the slope is 4. So the slope is 4, x to the 4n. But now if I plug 0 in for there, I get 0, and we want that value to be 2. So we just add 2. The denominators stayed as the odd factorials, because just because we're plugging something in for x doesn't mean the denominators are going to change. They're going to stay the same. That's 2n plus 1 factorial. Replacement. They call it substitution, same thing. The next example is multiplication. So let's start with cosine. Cosine is an even function, so that's x to the 0. X squared over 2 factorial, x to the 4th over 4 factorial, x to the 6th over 6 factorial. Keep on going. Let's multiply times x. So we'll multiply x on the left side. We'll multiply everything times x on the right side. So we distribute the x through. X minus x to the 3rd over 2 factorial, x to the 5th over 4 factorial, and then x to the 7th over 6 factorial. So let's get the nth term for this. So we'll start at 0. I mean, might as well. You can start at 1 also. -1 to the n. That starts us out as a positive, and that's what we want. We want to start as a positive. X to the, well, we're adding 2 every time. That's what gives us the odd numbers. So 2n, but if I plug 0 in for n here, I get 0. I want that to be 1. So plus 1 over 2n factorial. Now I want to make you think here. So far, all you had to do is just copy everything down. I'm going to make you think a little bit. I want you to change everything, or change what you would need to change if I decided to start with 1. What would that look like? No, right, like a new one. Yeah, that way you have that example still. Write a new one. Write a new one starting at 1 instead of 0. What would that look like? So that you get the same series. No, the -1 would have to be n plus 1 or n minus 1. Or n plus 23 or n minus 23, but I wouldn't make it that complicated, right? Just we need to offset it by 1, either way. X to the, well, I mean, the slope is still 2. But now if I plug 1 in, I get 2, and I want it to be 1. So that would have to be a minus 1 over, I mean, it's still, the slope is still 2 on the bottom, but I need to start with 0. So if I plug 1 into here, I'm minus 2. And I think that's a little uglier. It's not wrong. It's not more right or more wrong. It's just a little more uglier. Starting with 0 seems to be a little cleaner answer. Not a big deal. We're going to find the Maclaurin series for f of x equals e to the 2x. So f of 0 is, we'll just say it's e to the 2x. That's e to the 0, so that's 1. F prime of 0 is 2 e to the 2x. If I plug 0 in there, we just get 2. Right? Yeah. F second derivative is 4e to the 2x, and we get 4. And how about 2 more? That's going to be 8. And finally, how about a 4th derivative of 16 e to the 2x equals 16? On a Maclaurin series, 1 plus 2x plus 4 times x, I don't need parentheses here, we're centering at 0, 4x squared over 2 factorial, plus 8x to the third over 3 factorial, plus 16x to the fourth over 4 factorial, plus keep on going. So if I start with 0, it looks like it's 2 to the n, x to the n over n factorial. Use your answer to A to find a Maclaurin series for the function h, given that h prime is e to the 2x and h of 0 is equal to 3. That's called an initial value problem, so they're giving us an initial value to find the constant. So we want h, not f, h prime of x equal to this. And keep on going. We're not going to worry about the nth term on this part, not yet. Well, if we're given h prime, how do we find h of x? Integrate, right? We're going backwards. We're integrating. What we're going to do is called term-by-term integration. We're going to integrate each term, which is not as hard as it looks. Because you got to keep in mind that all these are just coefficients, right? And then we really just have x, x squared, x to the third, x to the fourth. That's what we'll have to take care of. And all the coefficients, they just tag along. Notice that when we write these polynomials with Taylor polynomials, we write them backwards, don't we? Because we have x to the fourth as the last one. Usually we write it as the first one. So when we integrate with indefinite integrals, what do we put at the very end? Plus c. So guess where we're going to put it now? At the very beginning, that's right. So we're going to go c plus integral of 1 is x, integral of 2x is x squared. Now it looks really complicated, but it's really easy if you know how to integrate fairly well. What do? We add 1 to the power, so that x squared becomes x to the third, but then we got to multiply by 1/3. Well, the coefficients that were already there just tag along. 4 and the 2 factorial tags along. So there's the antiderivative. And let's keep going with that. So then we have x to the fourth times 1/4, and the 8 and the 3 factorial tag along. And one more, x to the fifth over 5. So 1/5 x to the fifth is the antiderivative x to the fourth. We're going to bring this with it. Plus keep on going. But h of 0 is 3. So 3 is equal to c plus a bunch of zeros. Because when you plug 0 into all these, you're going to get 0. So c is equal to 3. They'll usually give you h of 0 for this. All right, so now we have h of x is equal to 3 plus x squared, plus look at this, 4x to the third over, isn't that 3 factorial? And 2 factorial times 3 is the same as 3 factorial. Plus 8x to the fourth over 4 factorial. Plus 16x to the fifth over 5 factorial, and so on. Now we're supposed to write the nth term. But we kind of, what if we start with n equals 0? We kind of have a problem because the pattern doesn't start until right there. Before it, I don't know how I'd fit 3x and x squared. I don't know how I'd fit that into the pattern. But that's okay. It's fine. We're just going to keep going. This is 2 squared, 2 to the third, 2 to the fourth. So we're going to write 2 to the n plus 2. because that's really 2 squared when I'm plugging in 0. X to the n plus 3 over n plus 3 factorial. Now, if we're going to write the sigma notation, it looks a little weird, but it's perfectly legal in Nebraska to write this. To say, well, the series looks like that at the very beginning, but then I can start summarizing. N equals 0 to infinity of 2 to the n plus 2, x to the n plus 3 over n plus 3 factorial. So if you look at a polynomial or a series, and boy, you just don't know how to fit those first few in, that's okay. It's not a problem. Just start the pattern where it starts, and you'll be fine. That'll be a good answer. Any questions on that? So integrate term by term. We do derivatives by term, substitution, multiplication. Find the Maclaurin series for f of x. Give the first 4 non-zero terms and a general term for each series. Go. Help each other out with your partner. You can turn around if you want, since your buddy's not here.
Where is that?
Oh, you guys don't have it?
I don't think so.
I don't have it. Oh, did I not hand the notes out yet? Oh, what? How long have you been on notes? You didn't tell me? Sorry. Oh, it just started, didn't it? Yeah. Okay, all right. I feel better. I've never seen a 6. Watching this, we can fast forward till you see me writing again.
I don't know. I don't know. That just. That one.
So this is e to the x. So let's start with e to the x. What I would do, that's 1 plus. Does it say give the first? Yeah, give the first 4 and then the general. X plus x squared 2 factorial, x to the third over 3 factorial equal to 4. I'm not going to worry about the nth term of just worry about the nth term of the last one, of the final product there. Speaking of product, 2x e to the x now is 2x plus 2x squared plus 2x to the third over 2 factorial plus 2x to the fourth over 3 factorial. So now we want the general term of this. So we distributed 2x through. It's multiplication. So we have a 2 on everything. What if I start with 0? X to the n plus 1 over n factorial. There we go. I'm going to do, we haven't done one of these yet. I'm going to do this one here. Always do replacement first. Don't multiply first. It's much harder. Replace first and then multiply. So let's start out with cosine. 1 minus x squared over 2 factorial. X to the 4th over 4 factorial. X to the 6th over 6 factorial. Replace first. So we're going to replace everything with 2x. They call it substitution. 1 minus 4x squared over 2 factorial plus 16x to the 4th over 4 factorial minus 64, yeah, 8 times 8. X to the 6th over 6 factorial. Plus, keep on going. And then we'll multiply. So x cosine of 2x is x minus 4x to the 3rd plus 16x to the 5th minus 64x to the 7th plus keep on going. All right, now we want the nth term of our final answer here. 1357. So if I decide to start with 0, and you can start with 1 also, wouldn't matter either way. It's alternating. And it starts with a positive, so I got the alternating part. X to the 2n plus 1. Because it's we're adding 2 every time. At 1357 over 2n factorial. Those stay even. Questions on this one? If not, try sine squared with your partner down at the bottom there. Sine of x squared, excuse me. Sine of x squared. Yeah. What are you starting with? 0? You're starting with 0?
Yeah.
Yes. Okay. Yeah, but that kind of defeats the purpose of actually multiplying the 2 x.
Okay.
So I would not do that.
Okay.
Because you really didn't do much other than the very first step.
No, I get you.
I would want you to distribute it. But isn't x times x to the n when you multiply you add the powers? So like 2 to the 3rd times 2 to the 4th is 2 to the 7th. There's a 1 up there. So that ends up being x to the n plus 1. And that's where you get the n plus 1. So technically it is the same, but I want you to actually do that process.
Because 0 is like 2x squared, and then 1 would be 4 plus 2, which is the same. 2 would be x to the 4th. Yeah, I guess so.
So sine's odd, right? It's odd. So let's go with just sine of x. So, x to the third over 3 factorial, x to the 5 over 5 factorial, x to the 7th over 7 factorial, plus keep on going. This is a replacement again, so we did one similar to this already. Sine of x squared is x squared minus x to the 6th plus x to the 10th minus x to the 14th. Now we want the nth term of this. X to the, if I start at 0, 4n plus 2. Oh, and I'm good at forgetting that it's alternating. I didn't forget last time, I forgot this time. Negative 1 to the n. There we go. There's the alternating part. Over 2n plus 1 factorial. It goes 1, 3, 5, 7. Am I missing something? I think I am. I think you are. Okay. What do you think you're missing? Figure it out. Yeah. Any questions on this? All right, so we're building from kind of that parent function, working our way to the answer. So we get out of here. Today happens to be a TA day. We're at 26. Oh, plenty of time. Construct the 5th order Taylor. Now, do we have anything? I think that's all the new stuff. This is all review. So building those Taylor polynomials, Taylor series, is the new stuff today. Make sure you have those memorized, and we'll talk about the others as we go. We already know geometric series, and the other one that you should have memorized is 1 over 1 minus x. That's 1 plus x squared plus x to the 3rd. It's x to the n. There's your geometric series. So I expect you know that one already. All right. Let's do a little review, and we'll call it good. Construct the 5th order Taylor polynomial, the Taylor series for the function at x equals 0. Use the polynomial to estimate f of 0.1. So here's the function. Now, this isn't a replacement because we don't usually or ever replace with a subtraction. If you look, we replace with 2x, and we replace with x squared here. We don't replace with 1 minus x. It doesn't work like that. So here we're going to do it the long way. F of 0, right? Because no, it's Taylor centered at 0, so it is a Maclaurin. E to the 1 minus x is e to the 1 minus 0, that's e. Then f prime of 0, we got to take the derivative. Derivative of e is e, but then times negative 1, times the derivative of the inside. So be aware of that chain rule all the time. Negative 1 e to the 1st, so e, so it's negative e. Second derivative is e to the 1 minus x. How many does it say? Construct the 5th order, but that's e. Looks like it's just alternating. So 3rd should be negative e, 4th should be e, and 5th should be negative e. Did I do that right? Positive, negative, positive, negative, positive, negative. Looks good. This is a polynomial, 5th degree Taylor polynomial. So we're switching. We talked about series going on forever. Now we're back to polynomial going, well, wait a minute, stop at the 5th degree. E. Not plus, minus. It's alternating. Minus e to, are we at 0? Yeah. All right. I'll get it. Plus ex squared over 2 factorial. Ex to the 3rd over 3 factorial. Ex to the 4th over 4 factorial. And finally, the last one, e to the 5th over 5 factorial. Now we get to kind of see if we did this right. So the approximation is, let me grab a calculator here. There is an E button. It's the second function of divide. E minus E times 0.1 plus E times 0.1 squared minus E times 0.1 to the third. But I forget divide by 2. Divide by 6 plus E to the 0.1 to the 4th. Divided by 24 minus E times 0.1 to the 5th. Divided by 1 twice. It's going to be a miracle if this is actually right. Okay, so then we go. Let's go E to the 1 minus 0.1. I don't know how I got that, but I got it. I don't know how that worked out. 2.459. 2.459. 6, 0, I can't remember. 3107. And, you know, that's great that we got this number there, but if you don't, I think if you don't actually find the what would we would call the actual value, you want to see if you got this correct. It's a nice little check. Then we can go on one more step and we can find the error. And we see it's very accurate. You know, it's accurate to 1, 2, 3, 4, 5 to 6, 7 decimal places. That's pretty darn accurate. Any questions? I think we'll stop.